Hey, hello everyone. Welcome to the module 2 on EHVAC transmission in power system 2 subject. In this lecture 1, we are going to introduce to the EHV transmission system. I am Ganesh from KKWAG Institute of Engineering Education and Research, Nashik. So what are the contents for the today's presentation? Role of the EHVAC transmission line in the power systems. Next, what are the standard transmission line voltages which are described by the standard IS standard? Then advantages and disadvantages of EHVAC transmission line. Then we will see what are the average line values parameters of the transmission line, then power handling capacity and line losses. So these are the contents of the presentation. So let's see what are the learning outcome through this session. At the end of this session, the learner will be able to elaborate the need of EHVAC transmission in India, identify the transmission system with voltage level, justify the advantages and disadvantages of EHVAC transmission line, and write the formula for power handling capacity and line losses in EHVAC transmission. So let's begin with the reflection point. So I'm putting one question in front of you. You have to answer that question. So pause the video and try to answer this question. Okay, so try to answer this question. Transferring power from generating station to the load center at generation level voltage leads to increasing voltage regulation, decreasing in efficiency, increasing in size of conductor, all of the above. So let's pause the video for some duration and try to answer this question. See, what is given in the question? If you transmit the voltage at the generating level voltage is starting from 11 kV to 13.8 kV. Suppose you transmit that voltage, you use the transmission level voltage also 11 to 13.8 kV, then this leads to which problem? Voltage regulation problem, efficiency problem, size of conductor problem, or all of the above? So pause the video and answer the question. Hope you have answered it correctly. So you will get the answer in the next discussion. So again, we will come to that, visit to that point. Okay. So increasing in the demand of electricity, increasing the generation with the tremendous rate. Okay. So as the demand is increases, the generation is also increases with the tremendous rate. But the bulk power station is very away from the load center. So take the example of Maharashtra. So we have a super thermal power station at the Chandrapur. Okay, so super thermal power station is at the Chandrapur, and maximum power utilization is happening in the western side of the Maharashtra, that is a Pune, Mumbai, Nashik, in this area. Then this bulk amount of power must be transferred from the generating station to the load center, so how we will transfer that power, that is the main challenge. Then need to transfer power from generating station to the load center, bulk amount of power must be transferred. Generation is happened at 11 kV to 13.8 kV. So using the generated voltage level for the transmission increases the losses. So let us consider that I am using the 11 kV which is at the Chandrapur station, 11 kV voltage Chandrapur station, and same I am using for the transmission purpose, and I am connecting the load at my end. So this is the load is required large current capacity, so the current carrying conductor size is increased. As the size is increased, the losses is also increased, and the R and L of this is will causes, and the large amount of current will causes a large voltage drop inside this line, hence the voltage regulation will become a poor. Suppose you transfer the 11 kV, at the end you might be get also 5 kV, so that is not acceptable. So if you use the generating voltage for the transmission of the power, it will increase the losses, it will decrease the efficiency, it will increase the voltage, also it will increase the size of conductors. So hope you got the answer which I was asked in the reflection point. Need of the transmission. So need of transmission of greater and greater amount of power over a long distance lead to the continuous increase in transmission voltage. Suppose you want to transfer the greater and greater amount of the power over a long distance, then it is necessary to increase the transmission line voltage. Okay, so this is necessary to increase the transmission line voltage. Hence, the present trend is to transmit the large amount of power over the medium and long transmission line at a very high voltages above 380 kV, called as the extra high voltage. So the voltage which are above 380 kV, it is called as the extra high voltage, which is used in the medium and long transmission line to transmit the large amount of power. So what are the standard transmission line voltages, standard transmission and EHV voltages? Voltage adopted for the transmission of bulk power have to confirm the standard specification formulated by all countries. All countries is having their own standards, international standards, so they have to satisfy that standards. So they are necessary in the view of import, export, and domestic manufacture and use. We need a various equipment for the EHV transmission substation. Okay, so that must be adaptable in the international level also. So we have to follow the national standard as well as the international standards while designing the voltages. Okay, as per IS, as per Indian standard 2026, India has adopted 132 kV voltage and higher voltages for the transmission line. So 132 kV voltage and higher is used for the primary transmission. The voltages which is above the 132 kV voltage lines is known as the HV voltages. Okay, and above the 320, above the 345 kV voltage, it is known as the extra high voltage. Okay, so that voltage is HV, EHV, and nowadays UHV transmission line we are using for the transmission the high amount of power from the generating station to the load center. The maximum operating voltage are also because in any cases. Okay, so what is the maximum operating voltage? Suppose we have designed the transmission line for 750 kV, but the equipment must be designed for greater than the 750 kV for the safety purpose. So that voltage is called as the maximum operating voltages. So maximum operating voltage is also very important point for designing of the equipments required for high voltage, extra high voltage transmission line. So according to standards, so how these transmission lines are classified? So nominal system voltage in a high voltage category 132 kV. Okay, so this is actually kV, it is 132 kV. This is also in kilovolt. 132 kV, 220 kV, 275 kV, and 345 kV. Okay, so and then in EHV transmission it is a 400 kV, 500 kV, 750 kV, then 1000 kV and 1150 kV. This is coming under the UHV category. So high voltage, extra high voltage, and ultra high voltage. But the maximum operating voltage is the for 132 kV equipment must be sustained with the 145 kV. For 220 kV equipment must be qualified for 245 kV. Likewise, so for the 1150 equipment must be standardized for 1200 kV. You know that in Nashik we have a 1200 kV testing lab which is designed by the Crompton Greaves, Nashik. Okay, so that is indoor, one of the indoor biggest lab is available for the testing of equipment of 1200 kV in India. So let's come again with the reflection point. Okay, so you pause the video and answer this question. What is the maximum voltage level available in India? So you can Google it also. So you try to answer. I will pause the video and you answer this. Whether it's 1200 kV, 1150 kV, 800 kV, or 400 kV. Okay, so you guess the answer. Yeah, hope you got the answer. So maximum voltage which is in India, maximum voltage level in the India is the 1200 kV, and that first line, first transmission line is going to be established between Aurangabad to Bina. Right? Aurangabad is in Maharashtra and Bina is in MP. So Aurangabad to Bina, this line is under construction. This line is under erection. Okay. So let's come to, I hope you got the answer correctly. So what are the advantages of EHV transmission line? Reduction in losses. So how this will reduction in the losses? If we increase the transmission voltage, suppose the voltage in the transformer, obviously we are going to use the transformer V1 and V2. Suppose V2 voltage is greater than the V1 voltage, so obviously I2 current is less than the I1 current. Means the current in the high voltage transmission line is less than the primary side current. So the current transmitted by this conductor is less. Hence, the electrical losses are also less. Hence, it increases the transmission line efficiency. Let's begin with the next. Improve in voltage regulation. So obviously if the current is reduced, every transmission line has RL parameters. So the voltage drop across this is nothing but I into R, and voltage drop across this is nothing but the I into XL. This both voltage drop is dependent on the current. This voltage drop will be reduced as the current is reduced. Hence, difference between the sending end voltage and receiving end voltage is less. That is, the regulation will be improved. We know that the regulation is calculated as mod of Vs minus mod of Vr upon mod of Vs. Sometimes it is used as mod of Vs upon A also, or in this formula. Okay, A is the transmission. We saw this in the last unit only. Let's begin next. Reduction in the conductor material requirement. As the current is reduced, so obviously the size of the conductor, the current carrying conductor, because we know that the current carrying conductor, as the current is reduced, the size of the conductor is also get reduced. Okay, somewhat this will increase the resistance, but that is not the problem. Okay, because the current carrying capacity is less, current is less, so the losses will reduce. It is the economical. So let's compare how it is the economical. Here I am taking the transmission line cost in on the x-axis and transmission voltages on the y-axis. Okay, so suppose we keep the transmission voltage low, so the loss in the cost of the energy will be very high, and transmission line terminal cost, that is the equipment cost, will be low for low voltages. Okay, equipment cost may be low, but your cost of the energy losses will be very high. As you goes on increasing in the voltage level, your cost of energy loss is going to be decreased, but your equipment cost is going to be EHVAC transmission equipment cost is going to be increased. Okay, suppose you calculate the total cost by adding these two, you will get this type of plot, and you will find that this is the most economical point you are getting, where this is the economical voltage level. So by using the high voltage, we will get the economical voltage level point, so which is the suitable for transmission system. So let's erase the which I have created here. Shall begin. So increase in the surge impedance loading. We know that the surge impedance loading is given by VPH square upon ZC. For the transmission line, this ZC may be around to 350 to 400 ohm, 350 to 450 ohm rather, you can say. And this, suppose we increase the voltage, the surge impedance loading is going to be increased. Okay, so surge impedance loading is going to be increased. Hence, this will increase the transmission line power carrying capability. Possibility of the interconnection of the systems. So in the high voltage, as the voltage is matched easily at the EHV substations, so we can connect the generating station, different generating station together with the EHV line. That is, the Chandrapur stations can be connected with the Koina substation, also can be connected with the Tarapur nuclear plant also, by using with the help of a high voltage transmission line, because the terminal voltage is approximately constant for that. Then increase in power transmission capability. As SIL is increased, SIL means surge impedance loading is increases, transmission capability is increases, because the transmission capability is given by power transmission line. Transmission capability is given as mod of Vs upon into Vr upon X into sine delta. So you know that the power transmission capability is almost proportional to the operating voltage square. So that is, it increases the power transfer capability also. Hope you got the correct explanation for this. Then reduction in the right of way. So what is this right of way? Suppose you want to transfer the 1000 megawatt power, and if you use the 11 kV as the option, then you will need n number of transmission line, and to install that n number of transmission line we need a large amount of area, land, that is a land area. Okay, and for every that land area you government have to pay. So that land acquisition will be a very big problem. We know that the land acquisition will be very big problem. So that right of way will be the very biggest problem. Suppose we using the low voltage for the transmission line. For the high voltage transmission line we need a less number of transmission lines, hence the right of way problem will be get reduced, because we need a less land for transmission of the same amount of the power. Connection of the remote generating station. So remote generating stations also can be connected with the main grid. But what are the disadvantage of the transmission line? We are going to discuss this disadvantage detail in the next, that is corona loss and radio interference. We are going to focus this on corona loss and radio interference in the next lecture. Okay, so we will not focus in this point. So how this will increase the corona loss and radio interference? Erection difficulty. Obviously, suppose we need we need very high voltages, high voltage towers, then to erect that tower we require a large number of material, and hilly areas, especially in the hilly areas, suppose you want to install a tower, or suppose in the sea also you want to install a tower, that will become a very biggest problem. That is erection problem is one of the challenge in case of, or you can say in the, so you can observe here. So in the hilly area, suppose you want to put this tower, so you have to bring this all material. The road is may not be available, so you have to bring that all material on the hilly areas to transmit the bulk amount of power. Heavy supporting structure, obviously it requires a very heavy supporting structure to hold that transmission line. Then insulation requirement. Okay, so as the voltage level is goes on increasing, the insulation requirement is also very high. The insulation requirement is very high. Then size and design, size and power station equipment design. Power station equipment size will be get increased, and the size also and the ratings also will be get increased, so that will be also biggest problem. So again we come to the reflection point, that is our tradition. Okay, so let's begin. Surge impedance loading. So how you calculate the surge impedance loading? Hope I have answered your question previously only. So these many formulas are given here. So how we will calculate the surge impedance loading of the transmission line for the three-phase transmission line? In the three-phase transmission line, how we will calculate the surge impedance loading? The surge impedance loading is given by, okay, so you pause the video and you answer the question. Okay, for the single phase, this is the answer. Okay, so you guess for the three phase. Hope you answered. This is the answer. Okay, so 3 VPH square upon Z is the answer. Hope you got the correct answer. Okay, so let's begin to the next point. So let's see the average. What are the average line parameters? The line parameters are very important for that. So let's see what are the average line parameters for this. So for a 400 kV transmission line, okay, with the 15-meter height and spacing between the conductor, means this tower height. Okay, this tower height is, total height is the 15-meter, and the conductor spacing, two conductors are placed apart from each other in the 12-meter distance. It is the bundle, so the bundle diameter conductor. Okay, so diameter of this bundled conductor will be 0.457. Okay, 0.457, okay, centimeter square. Okay, then what is the resistance at the 20 degrees Celsius? So obviously it is not a 20, it is 20 degrees Celsius. At the 20 degrees Celsius you will get the resistance is equal to 0.031 ohm. Inductance for that line is 0.0327 ohm per kilometer. X by R ratio is 10, means X divided by R ratio is approximately equal to 10. For the 750, we require a tower height as 18 meter and spacing between the conductor is 0.15. The diameter of the conductor is almost same, but if you observe that resistance is decreased over here and inductance is also decreased. So, and X by R ratio is 20. So as you goes on increasing in the system voltage, you will observe that X by R ratio goes on increasing. Inductance will going to remain constant, but your resistance is goes on decreasing. So what is your observation for 1100 and for 1200? There is no much difference in the parameter. So we have adopted the 1200 because we are getting the same benefit of the resistance and resistance. So we adopted the 1200 to transmit the bulk amount of the power. So 1200 will be, we have not adopted the 1000, we have adopted the 1200 transmission voltage. Okay, so that is the, okay, so that is the reason we are adopting the 1200, because 1000 and 1200 will give you the same parameter, but the benefit of the 1200 kV transmission line is very big. Okay, again this transmission line voltage is in kilovolt, so I don't know what happens to this. Okay, so this is a kilovolt. So generally line resistance is neglected. As you goes on increasing in the voltage, you will observe that X by R ratio is very high, means the resistance is very less as compared to your inductance. Hence the resistance may be neglected while calculating the power handling capacity. And it can be concluded from above, it can be easily concluded that higher voltage become, resistance becomes less. But keep in mind, the value of R, it is mentioned at the 20 degrees Celsius, but if you goes on increasing in the voltage, it goes on increasing in the temperature, your resistance is goes on increasing. So at a 50 degree, that resistance is get increased by 12.5%. We know that in the first year we have studied that RT is equal to R0 1 plus alpha 0 into T. That formula already we have studied in the first year only. That is effect of temperature on the conductor, that resistance of the conducting material goes on increasing as increasing in the temperature. So that will be the effect of temperature. So let's see what is happening in the power handling capacity. Let Vs and Vr are the line to line voltage. Keep in mind, I'm taking the line to line voltage. This is very important. Vs and Vr is the line to line voltage. Vs means sending in voltage and Vr means is the receiving in voltage. Delta is the phase angle difference between them. That is, suppose Vr is taken at the 0 degree Celsius, then obviously Vs is at the delta degree. Okay, Vs is at the delta degree. X is the positive sequence reactance per phase ohm per kilometer as per given in the above table. X is the positive sequence reactance of the line. L, capital L, here L is not the inductance, capital L is the length in kilometer. So you can take this length in terms of kilometer, because the inductance, inductive reactance is mentioned in terms of kilometer. Resistance of the transmission line is assumed to be negligible, because in the HV transmission line, X by R ratio is high. That is, X is very high as compared to R, or X is very high as compared to R. So resistance may be neglected. So how we will calculate it? Then the power handling capacity of the transmission line is given by, so how we will calculate the power handling capacity? Magnitude of sending in voltage into magnitude of receiving in voltage divided by X. X is the total inductance, but here X is given as a per kilometer, hence I am multiplying it with the length into sine delta, where delta is called. So try to plot this with respect to the delta. You will observe that with respect to delta, you will get the characteristics like this. Okay, so this is the power handling on this axis and delta on this. Can you tell me at what level, at what delta this power transfer will be maximum? At what delta this power transfer will be maximum? Obviously it is a 90 degree, because sine 90 is equal to, if you take the delta is equal to 90, then sine 90 is equal to 1, then power transfer P max is equal to mod of Vs into mod of Vr upon X into L. Okay, so that will be the formula for power transfer capability. Okay, so next, in EHV AC transmission line, generally the receiving end voltage, magnitude of the receiving end voltage and sending end voltage is same, because we are using the tap changing transformer in between, and so that magnitude of Vs and Vr is going to remain same. So let us consider it is equal to V. Then above formula can be modified as Vs and Vr is equal. So above formula can be modified by V square Lx into sine delta. But see that what we have concluded in the power delta curve, our power transfer is the maximum at the delta is equal to 90 degrees. So power transfer will be maximum at delta is equal. But for the stability reason, we are keeping delta at the 30 degree. Suppose we keep the delta is equal to 30 degrees. So sine of 30 is 0.5, means actually we are using the 50% capacity of the transmission line. So power transfer capability is the P max, but actually we are using the 0.5 of the Pmax. Okay, so 0.5 of the Pmax. So we are not going to test because of the stability reason. In the next year, we will come to know what are the concept of this stability. Let's come to the again reflection point. Okay, in a 400 kV transmission line with the 1000 kilometer length is having the reactance of 0.327 ohm per kilometer, maximum power transfer capability is. Here I have asked the maximum power transfer capability. Calculate it and answer the question. So these are the options. So pick up the correct option. Okay. So pause the video and answer the question. Okay. Hope you got the correct answer. What I have asked here, it is the Pmax is equal to V square upon x into L sine delta. Okay, sorry, sine delta will not come in this formula because delta is equal to 90 degrees, so sine delta will not come. So it is a 400 square, obviously it is a kilo, so kilo square is a mega. Okay, divided by x is the 0.327 into line length is the 1000 kilometer. Okay, so calculate it and answer the correct. Okay, answer the correct question. What is the power transfer capability of the transmission line? How to calculate the power loss? If the PT is the total power transfer required, then the number of circuit required. So P is the power handling capacity, and but I want to transfer this PT amount of power. P is the capacity of the line, and I want to transfer the PT amount of the power to the transmission line. I want to transfer the 1000 megawatt, but the line capacity may be only the 100 megawatt. So how many circuits are required? So number of circuits is equal to PT divided by P, that is 10,000 divided by 1000. So total 10 number of, sorry, 100. So 100, 10 cancel. So total 100 number of circuits. So 100 number of transmission line you will need, or 100 number of circuits are required to transfer the power. Okay. So that is the number of circuits. So how will calculate it? The power to be transmitted divided by power handling capacity. Then the current in the per phase current is given by the per phase current is equal to V into N. The number of circuits must be taken into account. Sine delta root 3 L into X. Okay, so that will be the current. So the power loss in the transmission line, how we'll calculate the power loss? So power loss is equal to 3I square. Total current is the I. So we know that. So let's how power loss in single phase circuit is equal to I square R. In the three phase circuit, we have to multiply it by 3. But here, such n number of having the R resistance, such n number of transmission lines are in parallel. Suppose n number of transmission line in parallel, what is the resistance, effective resistance? Let us consider that 3 ohm resistance, 3 ohm resistance, 3 ohm resistance are connected in parallel, all 3 ohm. So what is the equivalent? Equivalent will be 3 by 3, that is 1 ohm. So here also n number of resistances are connected, so equivalent resistance is reduced. In the parallel circuit, the equivalent resistance is always less than the smallest one. So here we have to divide it by n, and this resistance is in per kilometer, so it is a small r, so multiply with the length to get the total resistance. So this is the law, this is the what power loss formula. This is the what power loss formula. Then the percentage power loss as compared to the power transfer capacity, that is a P loss divided by total power transfer required into 100, that is the percentage power loss. Again, reflection point. In a 1200 kV transmission line with 800 kilometer length having the reactance of 0.317 ohm per kilometer is to be transmitted 10,000 megawatt of the power. How many circuits are required? Assume delta is equal to 3. Okay, so here the hint is first calculate the P. Okay, you know the formula of P, and then calculate the N. So number of circuit required. Okay, so pause the video and answer the questions. Okay, answer the questions, pause the video and answer the question. So I will not give the answer of this question, you calculate the answer of this question. Okay, so I will give you the formula only. Okay, so what you are getting here it is a 1200 square divided by 0.231 into 800 into sine of 30 degree. Okay, So you will get the P value, then power to be transmitted, that is a PT divided by P, it is a number, and it must be the integer on higher side. It must be on integer on higher side. So calculate it. Hope you got the correct answer. So pause the video and calculate it. Okay. So let's summarize together. EHV transmission system is useful for bulk power transfer with good efficiency and better voltage regulation. In India, 132 kV and above transmission line are known as, sorry, A is not here, so it is known as EHV transmission. Equipment and insulation level are governed by the maximum operating voltage. Equipment and insulation level designing is depending upon the maximum operating voltage. Corona equipment design and erection is the biggest problem in the EHV transmission line. Power handling capacity is the proportional to the square of voltage. Okay, so we are at the end of this session. Hope you enjoyed this session. Thank you. If you have any query, you can drop the message in the chat box. Thank you very much.